array of data, and then certain magic, black magic if you wish, happens. And so that those algorithms that we are searching for, we are trying to derive value from the data. So this is basically a simple recap what big data is. And then we use big data to drive automation. And you may have heard about V's of big data. According to different classification, big data is characterized by 3, 4, sometimes by 5 V's. And on this slide, I will show you how these characteristics of big data drive the automation, or at least my opinion on how this is happening. So the first V is variety. So here we refer to variety of different experiences, like, for example, products, services, processes that are offered to customers. So let's arrange these experiences on the x-axis. Naturally, we will strive to increase the variety of experiences offered on the market, as well. If you think about it, it indirectly suggests the level of development of a certain society. And the second V will be velocity, or the speed or the frequency of observing and capturing the data that relates to certain experience, right? So certain product, certain service, certain process. And we can plot velocity on the y-axis and arrange the different experiences on the x-axis according to their velocity, right? And then we gravitate those most frequent towards the left. And such a plot may form an exponential distribution. It actually may or may not. So let's assume it does. And we obtain the plot like the one you see on this slide. So the next V is value, right? So I already talked about value, so usefulness of these experiences. And then on the y-axis, we plot values which are function of velocity and value. So the experience get reshuffled from most frequent and valuable to infrequent and negligible, right? And of course, we will want to automate those that are more frequent and more valuable. So we can think of such a concept as a threshold at which we make a split of these experiences into those that are frequent and valuable, and we want to automate. We feel a pressing need to automate them now, and those for which we may postpone the automation. The next two V's are volume and veracity. So in order to achieve automation on a certain experience, we need to have a sufficient volume of data, right? In terms of gigabytes, terabytes. If you just have very little data, it just can be not enough in order to see insights, to make conclusions, to see some statistical trends in that data. So there must be simply some volume of data available. And in addition, we also need to ensure that data quality is in place. So the mapping between what we want and what we can automate doesn't really follow this sharp cut on the threshold, but it's rather blurred close to that threshold, right? So we can have something that we desperately want to automate, but we just, cannot because of the volume of data, of some of the characteristics of the data, quality, etc. Or maybe something is not really important to automate, but because we can, we do that. And last but not least, together with these 5 V properties, we should keep also one S in mind, and this is a skill. Right? So this is a skill, and if I click now here, that's reveals on the slide, and this is this S that stands here. So the V's of big data or data-driven automation. And right, so we may want to automate certain experience and even have all the required characteristics for associated available data, but we just may not have the skill, or we may just don't know how this can be done. And this skill may still need to be discovered. So I claim here strongly that modern automation is driven by data and insights we gain from data, and this is roughly the process we are following, right? And this snapshot can be refreshed in different moments in time, right? So this threshold moves, it's a dynamic concept, new experiences appear, the variety of experiences changes, something is already automated, something is not yet interesting for automation, becomes interesting at a later point in time, etc. So now let's take a look at the academic fields that are in our focus, so namely AI and BPM, and paying attention on how they promote automation. And to do that, I looked at some good books in both areas with the aim to understand how do they identify these disciplines, right? So for BPM, I looked at the book by Matthias Westke, who was my PhD supervisor, and this book was also the first book to give a comprehensive definition of BPM. And the first edition of this book was written at the time I was doing my PhD in Potsdam, and now it's in its second edition already. And the second book I looked at is the book by Marlon Dumas, Marcello La Rosa, Jan Mendling, and Haya Ryers. And the text that you see on the slide is the result of my attempt to synthesize definitions of main artifacts, main aims of BPM from these two books. So a business process is an orchestration of activities, resources, either human or computerized, of an organization. That, right, and this orchestration aims to achieve a present business objective. So here I would like to highlight this search for the balance between human and computerized resources. Clearly, one way to achieve the goals of BPM, which are concerned with improving the ways business processes are improved with the ultimate goal of reducing their costs, execution times, and failure rates, as you see on this slide, is through the delegation of human activities, which includes decision-making as well, right? So activities and also doing the intellectual work of decision-making to machines. So to those cyber-physical systems, sensors, networks, Internet of Things networks, etc. AI is then relatively a new field in science and engineering, and it has its charm due to the nature of the problem it attempts to solve, right? And it attempts to build these intelligent entities and systems that can simulate humans and animals, mainly their natural intelligence. So to understand the state of the art in AI, I looked then in the books by Stuart Russell and Peter Norwich, and also a very interesting recent book by Melanie Mitchell. And in the later book, the author argues that we still tend to overestimate the abilities of AI, and that today's AI is far from general intelligence. I thought, well, that's interesting, because, well, when I was doing my bachelor studies, roughly, well, not yet 20, but almost 20 years ago in Kiev, that was pretty much the same perception of AI. So AI still lacks a lot of abilities. And I still fully agree with this claim in 2020. But nevertheless, of course, we should acknowledge the recent developments that are happening in AI, especially in specific, these highly focused tasks where we observe that once required data is available, modern AI techniques, modern AI algorithms, they can outperform humans, or at least keep up with the performance of humans. So this ability to outperform or keep up with human performance when accomplishing tasks and taking decisions based on data can greatly impact the balance between human and computerized resources that participate in business processes, about which I talked on the previous slide. So if BPM and AI would truly meet, they will clearly both benefit. The benefits for BPM are, in my opinion, immediate, and therefore, well, almost obvious. They stem from this automation of specialized activities and decisions. So for instance, at the bottom of this slide, you see an example business process diagram, and in this diagram, certain activities, certain decisions are marked with well as a manual activities, manual decisions, and so these activities and decisions are then candidates for using AI techniques to automate them. So, for instance, the decision to take a thorough or a casual, simple check, right, can be done based on the some neural network, some convolutional neural network, which is trained on the data, and somebody is drawing on the slide. Thank you for that. Right. So based on some neural network that is trained on the appropriate data to carry out those decisions. So similar, like here on this slide, you see the network is trained to classify photos of cats and or other photos to identify if that is a cat or not a cat. So those specialized activities, right? They can be chatbots, for example. There's a lot of. Oh, sorry, I'm pointing to the wrong screen here. So chatbot or computer vision or speech recognition or speech generation. Those would be those specialized tasks that are not the general intelligence. They don't require general intelligence, and assuming also that you develop those chatbots, those speech recognition tools for a special domain in BPM or some business process that becomes even further specialized. And then, well, AI in its current state can cope with those challenges and derive the value for the business process management. All right. So if I would think about benefits that BPM can bring to AI, well, maybe it's probably not that immediate, but still I think there is something that can be transferred. So for example, we can use data-driven techniques from BPM, mainly proposed in the area of process mining, to learn those artifacts based on which then decisions are automated or semi-automated. So we can discover process models from data. We can do conformance checking to align reality and designed models, measure the quality of this model. So in that sense, we are contributing to explainable AI because we are creating artifacts from data which are explainable. So in process mining, we would strive to build models like this one in the bottom left to explain what is happening. And then those are, of course, inherently explainable to business analysts. And that's how we can build these artifacts that we can understand, we can then reason and think if we can trust them, if this is the ethical way of doing things, etc. So they can, if not maybe open completely, but give us a peek into this black box of AI, right? So not this black box where you get the input, the magic, this black magic happens inside of that black box, and then we get the output. So that's where I see that BPM can contribute the most to the area of AI at its current state of the art. All right. And just to emphasize process mining, because I told you that process mining is this data-driven area of BPM, right? So in process mining, the main data artifact is event log, which is a collection of events that are generated by IT systems, software systems that support business processes. Sorry, so support business processes in organizations. And okay, I just can hear some background noise. Okay, it's gone. So we generate event logs based on IT systems that support business processes at organizations. And then, so this is a sample event log. We can think of many attributes that we collect for different events that are stored in event logs, but usually we require that events have at least 3 attributes, so case ID, timestamp, and activity. at so business activity that happened, and then we will translate them in these cases or traces, right? So blue trace, which is also here denoted by blue rows, green case, which is denoted by green rows, and the reddish kind of case. And then this is our traces, and we will try to learn the models which have the structure which actually refer to the business activities that were happened, that are highly explainable. We will also try to understand the conformance of how well that model represents what was happening in reality and captured in the event log. So this is what we do in process mining, learning some insights from the data. And this area is heavily developed and driven by Professor Will van der Waals, who currently works in Aachen, which is in Germany. All right, so this was my introduction. So where BPM and AI can actually meet. And now I want to talk about two concrete examples of research in this intersection of BPM and AI that I was also involved in. And the first is on automated goal recognition. So goal recognition is a classical problem in AI, and what I will show to you is how we tackle this problem using techniques from process mining, right? So goal recognition consists in automatically detecting the goal an agent attempts to achieve. So for the first time, I was exposed to this problem in April 2018 when I attended a talk by a person from the Australian Air Force that took place at our school here in Melbourne. And this talk was about simulator of aircrafts and decision-making component of this simulation that should support pilots that need to recognize the goal the other aircrafts around are trying to achieve, right? And so these suggestions of what others are trying to achieve, then the pilot should be able to make a decision how that he himself should act in that situation. Should he attack? Should he continue patrolling the area? Go away? Etc. Etc. So this is the problem, and of course there are a lot of also peaceful applications to this problem, right? So let me just maybe introduce this problem in a more peaceful setting. So think of a grid where you have, well, cells, and you can walk in this grid, and there is a starting point, this initial point here denoted by capital I, and there are some goal cells, A, B, C, D, E, F, so there are 6 goals in our world, and you see two sample walks from initial state towards goal E, right? And the red one would be like a rational walk, right? So we first deviate from the trajectory towards our goal, and then we kind of go back to the trajectory towards our goal. And the green one is more or less rational behavior towards the goal. And what we do, right? So then we kind of should take these observations, put them in this black magic box, do some magic around, and we need to infer the probabilities of goals, right? So which goal is the most likely goal, and then, okay, accept that the most likely goal is actually the goal the agent is trying to achieve, right? So here you see that after each step, we reshuffle, we recompute the probabilities, and for the rational walk, which is a green walk, well, at some stage, the goal E starts to win clearly, right? And that's basically keeps like that towards the very end of the walk. And for the irrational walk, well, what we do, we first start and we think that the agent is going towards goal C, right? The green goal is goal C over here, and right. So these are first 5, 6 steps. So somewhere the agent is here, and we are thinking that that agent is going towards goal C, and then when we start to go into the right, slightly the probability of goal C declines, and the probability of goal E, the actual goal the agent achieves at the end, starts to rise and actually is shown to be there. So this is a general problem, and well, when we try to solve the problem, so first what we did, we looked at observational learning, and observational learning is learning that occurs through observing the behavior of others. So according to Bandura, and his social cognitive learning theory, there are 4 phases that influence observational learning, and these are attention, retention, motivation, and production. So you may have seen this video online where a mother duck goes on the stairs, and then the little ducklings try to follow the mommy duck, right? And so they observed, they paid their attention of what their mom has done. They retained that behavior in their memory. They were motivated to recreate this, repeat that behavior. So they were producing that behavior, so failing at the start, but eventually reaching their goal there, right? And this type of learning is actually doesn't need reinforcement in many cases. So we took these 4 phases as the general framework and kind of conceptualized it a bit further and developed this framework, which we published earlier this year. It's a framework for goal recognition, which is inspired by this principle of observational learning. It was published in AMS 2020 conference. And basically, right, so this framework is composed of these 4 phases: attention, retention, motivation. But instead of production, we are not really repeating the behavior. We are just recognizing the behavior of others based on what we learned. And each of these phases then has certain workflows, right, that, well, recreate the behavior that should take place in that phase. So this framework is defined from the point of view of some intelligent agent that observes and learns from agents around. And later, when the learning has happened, that agent is able to take decisions about which goals the observed agent is trying to achieve, right? So for example, what we need to do, well, during the attention phase, we need to capture those actions that we observe by, for example, by agent A, we observe action S, by agent B, we observe action B is done. And also we need to be able to recognize that there is some goal completion. So for example, agent A has achieved goal alpha, etc. And then in that retention phase, we will capture that action, we will append it to the trace, to the current execution trace of agent B or agent A, depending on which agent we are currently observing. And at some stage, we will observe that the goal is achieved. We will retain that trace into the skill library, and then we can learn the model, which we call the skill model from this data. And that will be our knowledge about how certain goals can be achieved. And then at the motivation phase, the agent decides, okay, now I want to recognize certain goal, and if that decision is happening, well, we are appealing to our retained memory of what has happened. We then kind of check conformance of what we know about the skills to achieve different goals and what we observe currently, and then we infer our goals. So basically, we then instantiated this framework with process mining techniques, right? So we observe many trajectories towards different goals in our grid, and we learn a skill model, like a Petri net, using the process discovery techniques from process mining, which captures the behavior towards a certain goal. I think this one captures towards goal A, the behavior towards goal A. And then once we observe a new trace, and once we observe a new behavior in our environment, we do conformance. We kind of say, where are the skills and the observations deviate, where they coincide, and based on this knowledge, we then propose a mathematical model that allows us to derive this probability distribution. So this was the paper published at AMS conference, as I told you, called Goal Recognition Using Off-the-Shelf Process Mining Techniques. So we were just taking available techniques and composing Z solutions and testing how good that solution can perform. That was basically the idea of that paper. If I can just go quickly through the steps. So we take the observations, we compose event logs. So for each observations towards certain goals, for example, all the blue arrows, all the blue walks towards goal A gets collected in the event log for that goal A. All the dark red walks get collected in event log B, etc. And note here that we don't actually need to know information about the environment we operate in. So this is also very different from available techniques in goal recognitions, which will often require the full knowledge. Here we just observe, and what we observe we know, right? So that's a very different aspect that's we have in our approach. Then we take event log, for example, for goal A, and we construct a process model, the skill model of how to achieve that goal. Right, so it's actually, if you look closely at it, you understand that this is highly explainable. So right, so from the initial state, we can either go north, so we have here an arrow, or we can go north, west in this case, etc. So we kind of can explain what is happening based on this model. This one was constructed using split minor, developed by Adriano Augusto, who is also a member of our group, but also in the evaluation we used transition system minor. They were developed by Eric Verbeek in Eindhoven. So we learned the skill models, and then when we observe this new fragment, new behavior, we perform the conformance checking. We construct such conformance diagnostic between the currently observed trace and the skill model. Actually, we do that for each of the skill model to assess them to which of the skill models the current observations align the most. Right? So here, if I explain this artifact a bit more, so the top two rows of this table, they correspond to observed actions. So right, so the agent was going north, north, west, northwest, and north, north again. Right, so this is where the agent was going north, northwest, northwest, north, north. So these are the observations of the agent, and this is what model can support. So in the model, I can also go north, northwest, northwest, but then I cannot continue to mimic the behavior of the agent. So now the observations and the skills that we know deviate. So and the best explainable correspondence between observations and the skills is that the model needs to continue by going northwest 3 more times. So if I go back to the model, where is that? It's here. So the model can do north, northwest, but then I can just complete the whole execution by going northwest. Well, actually, sorry, I go north, northwest, northwest once again, and this is exactly what agent is doing, observed agent is doing, but then the model needs to continue by going northwest, northwest, northwest 3 times, and then kind of we're reaching the goal. So this artifact, it's a technique is called optimal alignments, a well-known technique in process mining. We can compute the smallest deviations between observations and the skills. And then, right, so we can also have some costs on different steps. So, for example, the bad move costs us something. For example, the move to the north costs us $1 Australian, and diagonal move then costs us the square root of 2, right? If we assume that the going north, west, east costs us $1, then the diagonal move will be a square root of $2, which is 1.41 cents. Etc. We can search for such optimal alignments, so alignments which have the smallest cost. And then we use these alignments to compute the weights, and these weights, they are kind of another layer of abstractions that now have the logic of explaining the likelihood that the agent is trying to achieve certain goals. So basically it's a scary formula. I'll not go into depth into here, but there are 4 parameters we try to control here. So phi will be some constant which smoothens the likelihood, right? So if we will start with 0, let's say weight, and from initial state the agent takes some move, and let's say it takes a move according to one skill towards one goal, but deviates from all others. So then basically the difference between that goal and all others becomes kind of infinity, 0 and something. So we need to smoothen that, and that's the factor phi rho. Also, we penalize asynchronous suffix. So these moves that are asynchronous at the end, we say that they should be penalized more because, well, if at the end the agent deviates from the goal and is persistent in that deviation, it's most likely that the agent wants to go away from that goal, and these parameters lambda and m, they allow us to control that, etc., etc. So there are these factors. I'll not go in details in all of them. So basically, also, right. So this I is then the number of the number of the step we are observing, and the later we are in the trace, the more weight we give to that step. So if it's aligned or misaligned, if it's misaligned step and it's already the step number 10, already long way through the walk, well, that's more costly deviation, right? So from the goal, etc. So here are some examples. So right, so if I compute alignment weight for the first 3 steps, which are completely aligned, and for these parameters, so phi or 50, well, there will be 50. Everything else is aligned. The weight of that trajectory is 50. But then if I compute my weight for this complete trace of 5 steps, then, well, I'll have my 50 cost, which is a smoothing factor. But then we also have 2 steps at the end which misalign, and also will penalize some deviations here. So 4th and 5th steps deviated, so there'll be some weight of 52.8. Well, think of this just as numbers, which encode somehow that logic of where we want to put the emphasis on corresponding or misaligned moves. And then we given these alignment weights, which we compute for each of the skill models, for each of the goals. We then use Boltzmann distribution to derive distribution over all the goals, right? So the probability of a goal given the observation tau, this is a trace we observe, is computed according to the Boltzmann distribution. Well, why? Well, basically because my colleagues who are experts in goal recognition suggest that this is state-of-the-art way of doing this in AI area for recognizing the goal, and also it allows us to use this parameter bit beta over here, which is like a temperature that controls the level of confidence of the goal recognition we are doing. So it can also be interpreted as a trust over the learned models that we constructed from the data. So we obtain this probability distribution, and then goal C here is the winning goal. So we suggest that probably at that stage, at 5 steps through the walk, the agent, so my mouse keeps disappearing, the agent is most likely is walking towards goal C. We did some evaluation with real data, with the community from BPM and process mining will be very well aware about this data. We looked at daily activities of daily living. This log was made available in one of the papers, right? And also we had the logs for Dutch municipalities for doing the building permits and environmental permits. So that those logs contain business processes of 5 municipalities in the Netherlands and how they were basically handling different processes in those municipalities. So by observing certain fragments of those logs, we were trying to guess, to predict towards which municipality that goal is now taking place, so in which municipality that business process is now executed. And also we did some synthetic evaluations using planning domains from AI, from navigation, so walking in the grid as I showed to you, and also blocks world, where you have basically a pile of blocks and you want to reach some configuration of those piles, and there are some rules where you basically understand how you can move the blocks, how you can lift them, where you can put them, etc., to achieve your desired configuration. So we took the constraints of those worlds. Basically, those constraints completely describe the world, and we simulated some sample traces and use those traces as potential observations, like observations of behavior, and we learn skill models, and then using new observations, we are trying to recognize the goals. So for the real life domains, we then, we just understood that we are performing better. We actually didn't have a baseline to compare with. Well, our recognized goals are doing better than the random guess, so to say. So precision recall we see is much better than random guess. If talking about planning domains, we also did some different configurations of our worlds. So let's say we had different number of goals, different grid sizes, trace optimality for learning or for training and testing the goal recognition, observed percentage. So we were observing partial traces, not the full trace, but let's say 50% of steps in the trace, number of training traces that we used, etc. And then what we observed that, right, with a different behavior of the factors. So if we increase the number of goals, if the number of goals go up, then performance goes down, right? In the world, the more goals we have in that world, the more congested the works in that world is, and the harder it is to discriminate between different goals. But if we increase the grid size, for example, then we, the works become more sparse, it's easier to do goal recognition, so performance goes up. The more optimal are the traces, the less they deviate from the optimal trajectory, the better the performance. The higher the percentage of observations, the better the performance. The more the training we do, the better the performance. So these are the kind of observations we had. We compared with some techniques in goal recognition that use planning and the knowledge of full world. We often observe that we are faster in performance to do goal recognition, but also lower in recall, as our approach doesn't rely on full knowledge of the world, right? So there are some pros and cons, and currently we are working further in doing the comparisons and trying to understand how can we tune the parameters of our model, and when one parameter is more important in which situation it leads to better results, right? So the paper was written together with my colleague Nir Lipovetsky here at Melbourne, who actually working on planning, with Sebastian Sardina from RMIT University, also here in Melbourne, and also with Zihan Su, who is a student, and he recently started a PhD on this topic. So we hope to continue with this line of research. All right, so this was one application area, and I would also like to demonstrate you another application area, which is robotic process mining. Recently, it is also referred to as task mining. Basically, Gartner is advertising this term very strongly. I know I have a lot of physical robots on this slide, but it is actually about software robots that I want to talk about. So robotic process mining aims to automate, it aims to automate robotic process automation. That's the very correct way of putting it. So RPA automates, robotic process automation automates repetitive clerical work by executing scripts, or also called RPA bots. So what can be that repetitive clerical work? For example, transferring data from one system to another, from Excel form to a web form. And actually, this is not fiction. This really happens in life. We also observed this in University of Melbourne. Our enrollment team does a lot of this manual work on transferring data from Excel forms into our systems. And then there is also the RPA team that helps them to automate these routines that they're doing. Right, so here you see this form in Excel with student information, and then you need to transfer this information into the web form, and then click submit, and then this information is stored in the information system. And so how it's done at this moment, so how do we do RPA now? There are solutions, there is big industry behind this. So what is suggested is that we observe interactions of users with information systems. So basically we observe what is clicked, what is copied, where it is pasted, which button is clicked in the UI. So, and through these observations, we kind of identify routines, and then we call those routines into the RPA scripts. So little programs, little scripts that now do this data manipulations in the information systems in the UI automatically. And so this is, of course, is a very error prone. We should do it offline, kind of difficult to maintain, mainly because of a big lag between observations, acquiring these observations, and coding, and then actually putting this into practice. And this is it can be quite a lengthy process. You can be very late with your RPA script because already, well, the format of data changed, etc. So what we propose is to forget about this manual, mostly manual observations of how work is done, and record automatically what is happening into so-called UI logs, and then use those UI logs to identify routines automatically. And once we identify those routines automatically, we also don't code them manually, but we discover models, then later we compile into those executable RPA scripts. So this is our idea, our vision for automated robotic process automation, right, so that's our term, robotic process mining. This is basically the picture of robotic process mining, and it is data driven. You can do it online, you can do it just as you go, as you click in your system, and then the system can automatically suggest you, look, you are repeating this very often, do you want to automate that? It's very flexible because if your work practices change, if kind of data format changes, you can quickly readapt, etc. We have a team behind this, so it's not me alone who working on this. So we have a PhD student, Volodymyr Leno, who drives this line of research. Also, we supervise Volodymyr with Marcello La Rosa here in Melbourne, and also there are two external supervisors, Marlon Dumas and Fabrizio Maria Maggi. And the first paper we published on this topic was Robotic Process Mining Vision and Challenges, published in Business Information Systems Engineering Journal. And in that paper, in that article, we summarized the pipeline of how to get from those observations that are happening, inherently happening in the real world, to the RPA scripts. And basically, this is a pipeline of different problems that need to be solved. And once you solve this problem along the pipeline, you derive at an RPA script. So you start with recording what you observe, then you segment it into the traces because, well, you record a continuous trace, right? So you don't have this notion of start and end of a business process. You really record, let's say, a session of work in the course of a day, and then you need to segment that, then you need to simplify, you throw out some non-value added step, then you identify candidate routines that you think what is executable, then you compile, and then you derive an RPA script. So we also have tool support. So first we worked on the action logger to record those UI logs at the level of abstraction of actions that we can then later take forward and automate. And we published that tool and discussed that tool in the paper at the BPM conference at the demo session last year. It's called Action Logger. And this year, I think on Wednesday, Volodymyr will present Probidium, a tool which then supports all the subsequent phases and implements the results of our theoretical work on how to solve these different steps of this pipeline. And these are the theoretical results of a lot of publications on different steps. The most techniques we were developing to discover this executable routines or subroutines. So you see this very intensive. There are 3 papers here listed, but kind of we now achieved the first coverage of the whole pipeline. So this is the UI logs we record. I'll just say a few words about some of the steps of this pipeline. Right, so in addition to those 3 usual suspects of the events in the event log, so case, actually there is no case ID here. So in addition to timestamp and action, right, so we will not have case ID, and because this is a continuous trace, and also there will be a different payload of other attributes that we believe are important. So let's say which cell in the worksheet was clicked, what was the field value, etc. So there are additional attributes which you need to collect in order to then support the use case of RPA. And that's what this our tool action logger is doing. It collects that UI logs, it records those UI logs. Then this year at ICPM conference in October, Volodymyr will present our work on segmentations. And once we now have this continuous trace, we need to cut it, we need to segment it into these small chunks, small exercises of transferring information for one student from Excel form into the web form. And what we do, just in a nutshell, we construct the directly follows graphs, where vertices are actions and edges are the immediate follows relationships between the actions that we observed. And then we identify strongly connected components, right? So those strongly connected components denote repetitive behaviors, and then through the dominator tree, so the entrance to the strongly connected components and the back edge, which tells us, okay, you return to the same behavior again, we then segment this continuous trace into multiple smaller segments. And well, to learn more about this, I would suggest you to follow the presentation of Volodymyr later in October. So then also we need to automate a lot of data transformation. So for example, this is a snippet of this UI log. I showed you several slides before. And here you see that, well, we manipulate the phone number, right? We copy it, we paste it, and also then we edit it already in the web form. We edit it, and we remove the country code. We replace space characters with dashes, with minus characters, etc. So how do we automate this, right? If we have one format of data as input and the other format of data as output, we also had a paper on that. So basically, we look at the whole task of transferring the data as a big transformation, where for certain fields, we will do the joining of the data elements, right? So for example, here we concatenate first name and last name. Sometimes, I don't see where, sometimes we will split the data. For example, address will get split across multiple fields in the web form. Sometimes we will actually copy, paste, and edit the information as shown here in this field of the web form. So how can we actually automate all of that? And for that, we looked at existing techniques that aim at automation of such data transformations. So basically what we do, we take the whole input and output as 2 big chunks of data. And right, so they are, of course, in different formats. They can be split, joined together, different transformations can be happening. And then we are trying to discover the transformations from input to output. And we use the approaches, techniques from program synthesis, which basically composes that trajectory from input to output of operations that you need to perform in order to get the transformation right. As of here, we need to split the input, the phone, based on the space character. So we need to want to do this based on the first space character. So we have the country code separate from the rest, and then we need to drop the element 0 to get the output. So this is one way of achieving the output from the input. Other way is that we split the input based on space. So we do the big splitting of all the parts. We drop the country code, element 0, and then we join once. So joining the first and second column, and then joining the two remaining columns and arriving at the output. And so there are multiple ways. So there's kind of a search that is happening here, and then we select the one that requires least number of steps. That's our then transformations that we are then automating into a script. And of course, so this is very nice, very simple, but also we have two optimizations, because in general that can run forever because the search space is quite big. So in the paper that I showed, that I listed on the previous slide, somewhere on the previous slide over here, in this paper, which we presented this year, believe me, not in New York, in February, we were still there physically, and then the lockdown started to well, happen across the world. So in that paper, we presented two optimizations. How can we use domain knowledge about the data in order to speed up the computations? And actually, the results that we obtained were quite good. So we were able to construct this transformation really, really fast, or sufficiently fast for our purposes. And then we automate the script. So in the video tool that will be presented, I think on Wednesday, if Vladimir is here, he can maybe correct me. So in the demo session, we then also generate the executable scripts. So currently the tool generates scripts for UiPath, which is a product for RPA. And those scripts can be executed, and we can carry out those scripts automatically. So this is basically my last slide. This is what we do on the side of RPA. It's an area which was researched in business process management, recently got attention from AI community. So the papers that we presented in New York was presented at IPA, Intelligent Process Automation workshop. So first workshop that happened collocated with AI conference. And also I know that there is RPA4BPM this year, and one of the papers, I think that was accepted there, also talks about the kind of results of that workshop and some insights that were gained in that workshop in New York. All right, and this is really the last slide that I have. I listed some challenges and opportunities. I think there are a lot of opportunities to automate. So the challenge is to automate these mid and highly intellectual activities and decisions. Another challenge is to identify data suitable for automation. So do we have enough data from which we can learn inside? Do we have too much data which harms our automation? We can learn a lot from BPM for doing explainable, ethical, trusting AI. We can also learn from process mining and the quality measures that are developed in process mining to understand if the models we are constructing, both in BPM and AI, if they give us good generalization, or at least reuse the principles from process mining to do that. So through quality measures that are offered in process mining, but also other quality measures can be a big challenge to define and propose those quality measures that can assess how good the derived artifacts are. Also, forecasting business processes using AI is a very hot topic. A lot of work is done, but I believe also this area requires much more attention. Okay, I was not following the time, but this is the end of my talk. This is what I was planning to say, and I think I roughly used 1 hour to do that, so that's very good. So thank you for your attention, and if you have questions, I'm happy to answer them.
Thanks, Artem. You have been perfect with the time. Yes, it's time for questions. So to ask questions, I invite the audience all to write your name in the chat so I can unmute you. And you ask question real time to Artem or to raise your hand in Zoom. So I can mute you as well. Let's see if we have questions. I can start with one question because I have one, since I'm, as you know, I'm working with a PhD student of mine on RPA as well. So I'm very interested in the topic of the data transformation. My question is, how can you map the input that have similar behavior to then map them? So I can identify this input with similar behavior and then apply the data transformation just to that input.
So how, well, I'm not sure I understood the question. I'll try to answer. So, right, so because we do the segmentation, that's a way of understanding the similar behavior. So we have this continuous trace, and then we cut it into these fragments, segments, which expose the same behavior. And we assume that within that same behavior, which is a segment, we roughly do a same automation, so same data transformation, right? So that's how we narrow down the scope where the inputs and outputs are. So then the inputs and outputs happen within the same segment, right? So then we can, through our UI logger, we can observe all the actions that took place, and some of them are copies, so read operations, some of the paste, write operations, and then we can kind of construct the problem of doing the data transformation. And so using all those components, segmentation, and then observing what is actually happening inside of each of the segments, we are composing a lot of instances of transformations. And then based on these instances of transformations, we learn the model of the transformation that happens.
Okay, okay, it's quite clear. So I have to disappear, by the way.
I invite you too, thank you. Yeah.
Other questions? Oh, there is Matthias. Okay, please.
Thanks. Yeah, Artem, thanks very much. Very interesting presentation, as always, I have to say. I have a question on the RPA mining part. So it seems that you are looking at the log that is being produced. And I was wondering, because often it's the case that I work in a process, I start with one activity, I do certain things, then I'm jumping to another process instance, I do other things for that instance, and then at some later point, I come back to the first instance again. So are there thoughts about investigating these types of overarching process? Because now you're looking basically at one activity, and you look at the internal process of that activity. So how about this larger scope of RPA?
Thank you for the question. Very good question. Yeah, we are continuously thinking about this. And of course, right, when it's just one task, I just transfer data from web form to from Excel form to a web form. That's straightforward, and you expect to see one type of behavior inside. So, but also, if you have a larger scope, I think what helps there is statistics. Statistics helps you to identify the different frequent fragments. Or repetitive behaviors. So, right, it is routine, right? It is routine we are looking for. Routine is something you do over and over again, right? So I have, let's say, 50 students to transfer, and through that repetition, I should be able to see that, and maybe not all of the 50, but 47, I did exactly the same thing, because it's actually convenient for me. And if I am just very creative in that, well, too bad for the user. I don't identify the repetition, and I am not able to then automate that, right? So then we will wait for the next day when the user will be maybe not that creative or follow the same trend, and the activities will be packed into one chunk of time. But also, if you kind of switch, also we hope that the switch is not happening often, and you can see some statistical trends that now I am doing, let's say, transferring of data from Excel into web forms for student enrollments, and now I am in my head of coordinating IT students here in Melbourne, and I'm answering some emails which are of similar patterns, a similar template. I can just automate maybe even that activity, right? So I'll again have a chunk of time where I'll be persistent in that activity of doing the task of answering emails. And if I try to segment this now long trace, long recording, which contains both, well, if I construct this directly follows graph, maybe these two behaviors are now encoded in two different strongly connected components. Well, they probably should, right? And I can, to some extent, identify them. It's not guaranteed. We haven't really experimented a lot of them, but it's a very interesting problem to look at.
Okay. Thanks, Adam. Thanks.
Okay, so I have, so I'm unmuting Bernardo Nugro that he has a question for you.
Oh, hello, hello.
Hello, yes.
Can you hear my voice?
Yeah, I hear you very well.
Yeah, okay, thank you for your presentation. So I saw one of your slides mentioning about the NLP and BPM. So is there any additional insight? What's the relationship between the NLP and BPM?
Between NLP and BPM, well, I was mainly on that slide, well, slide number 8, I think, or something. Anyway, I'll not search for it. So there are a lot of problems that AI tries to solve, right? And they are often very specialized. And that I'm not sure if I had NLP exactly. I was more thinking about speech recognition, speech generation, this type of things that can be reused in the business process management, right? Where I can, for example, make an automated call and read some information to the customer, so I don't need a human being involved. Right? So these things, natural language processing, well, probably there are some business processes that benefit from it. I don't have it immediately in my mind. I think on the slide I had speech recognition, speech generation, not NLP. But probably there are some possibilities to do translation of text using NLP techniques, right? It's very active recently. Very active research in AI, especially, right? In the AI area. We had here several talks recently. Now we're giving some interesting insights into that problem. But yeah, let's say language translation. I need to translate a text as a human step, manual step. I can now automate it using NLP technique to some extent, to some reasonable quality level.
I see. Okay, thank you. Thank you very much.
Thank you for the question.
Okay, next question by Joseph Carmona. So, Joseph, if you're there, you
can you hear me?
Yeah.
Yes, Joseph, I hear you very well.
Thank you very much, Artem, for this nice presentation. This is a very nice overview, and I think it was at some point very technical, which was helpful, at least for me. So thank you very much. I have a question on the especially on the goal recognition. A couple of questions there. So the first one is, as you said, the conclusion that you had is that you are better on performance with respect to the other techniques on goal recognition, but you lack a bit the context in a way. So you don't have. So I was wondering whether so moving to multi-perspective process model and therefore multi-perspective conformance checking can help you to get closer on that direction. That is one question, and the other question was on the models that the goal models you extract. You have many label splitting there, so you have very few labels like going up, going down, and then you have them scattered along the model. And I had a question there. So if there is a particular goal in order to split labels with the technique you have used to discover the process model, so that you control a bit. I guess if you said that you were using the the transition system miner. So I guess you want something which is very fitting the trajectories you have observed. So if you can say a few more words on how you control the label splitting in these discovered process models. So thanks a lot.
Thank you, Joseph. I'll start from the second question. I'm not sure what you mean by label splitting, right? So we had very clear steps, right? So going up, so very clear operations. I mean, the problem of actually recognizing the actions in the environment was kind of left out. We were assuming we know the actions that are happening, the move up, move left, move north, west, etc. And we were aiming not really necessarily for fitting models. We were actually hoping that we will be gaining something from generalization, right? So that this discovery techniques that we'll be using will generalize the data, and then we will be able to kind of get the benefit of that generalization, right? So this was our hope.
Okay.
To some extent, we observed that. I can't say that we kind of were successful in doing that, but we observed that. Also, but also one lesson, what we learned is that so these data sets that we had for working in this grid, they were quite complex and quite well. They put a lot of challenges for the state-of-the-art discovery techniques. So we played with inductive miner, with split miner, we played with transition system miner, and sometimes we observed that we were actually not benefiting from using inductive miner because at some stage we were starting to get too much of generalization. And so it was because if we had a lot of traces, which had a lot of variability, like in the case of a walk which is not really going close to the optimal path, but deviates from it about 30% far, you can already have a lot of variability there, 30% from optimal, you very quickly generalize too much, right? And you basically get the almost a flower model, right, with all possible traces accepted. Probably this is because the goal is to explain this to the business analyst, so you don't want to create a big model. For us, it's good if you can explain, but if you can just learn it in a good way, so you get a useful model and you will never read it, you just keep it in memory as a skill model, you don't need to read it every day, so to say, or discuss it with your colleagues. So a bit that we were missing. So we observed generalization, but sometimes it was too much of generalization. Fitness, yes, we were going also for fitness, but haven't had a problem with that, I would say. So split miner was sometimes slow on big data sets. We experienced. So transition system miner actually that we used was the best fit. That's why we use it for the evaluation at the end, for the full evaluation. But again, this is maybe the particularities of the data set that we were using. And the first question, sorry, I forgot, what was that first question?
About using multi-perspective discovery and conformance, so that you can cover also the part that you are currently missing.
So the more information we can get from data, the better. So multi-perspective data perspective, extremely important. So recently we started working on stochastic process mining. I think this is a crime not to, to use frequencies of observations that we have in the event log, construct models based on frequencies, but then take them and throw them in a garbage bin and just have a control flow model. This is just a crime. I mean, we have this data readily available, it's valuable data. We used it in construction of the process model, and then we kind of said, yeah, this is a model, but now, I don't know, was the decision going right or left 99% versus 1% or 50-50? I forget about this. This is, I don't understand why we are doing that. I think we should try to keep as much information, which we believe is correct information, in the model. So likelihoods, probabilities, but also data decisions, if we can learn them, we should keep them. Because that's then will be more correct representation of reality.
Thanks.
Yeah. Thank you, Joseph.
Okay, thank you, Joseph. We have time for a very last question before the break. The question is from Ahmed Awad. Ahmed, if you are there, you can ask the question directly to Artem.
Yeah, thank you. Can you hear me?
Yes, Ahmed, I can hear you.
Yeah, how are you? Thank you very much, Artem, for this interesting talk. Actually, my question is motivated by your first few slides about big data and how they can guide or motivate what to make and what to not. And I would just want to think about how these challenges or these landscapes, if you have experienced some limitations with your experiments with these big data sets with currently available tools, or how you see that what would need to be developed or what need to be tackled in this area to cope with these large sizes of big data sets. Thank you.
Yeah, so thank you, Ahmed. Thank you very much for this question. It was very bad connection. I think I just managed to grasp some of the
Artem, sorry, you should, the question is also on the chat. You can see it.
Okay. I just don't see the chat. I see.
No, the question is, how do you see the 5S of big data affecting the process mining tools landscape?
Yeah, so okay, so yes, this was the thinking of. So, so of course we observed that, right? So even with this experiment that I currently show on the slide, right? So if we had very little data, so volume was not enough, performance was bad, right? We need to increase the volume. If we had, let's say, also observed percentage of observation was low, we also had a performance drop. If we had too much data, like I talked to this, the last slide, I had this bullet point, so you need to, like the data that fits the purpose, you don't need extra data. If we had too much data, we were getting flower models, so we were losing the usefulness of models, we were generalizing too much. So there must be this balance, and you need to search, and then the challenge is to search for that balance. So yeah, we definitely observed all kind of the interplay between characteristics, these different characteristics of data that I discussed, these 5 V's: volume, veracity, variability, value, etc. Maybe not all of them, because some aspects we are not modifying, we are not changing. Like, for example, the trust in data quality, we're assuming data is good, of good quality. Right? So we're not experimenting with that one. But it's a good idea to do such experiments. Yeah. So I hope this answers, if I understood the question correctly. Thank you, Ahmed. Thank you very much. Nice to hear you.
Yeah, that's okay. Thank you very much.
Thank you. At this point, I think we can close the session. Thank you again, Artem, for your nice presentation. So we have to celebrate.
Thank you.
Thank you.
Thank you once again for inviting. Thank you, the audience. See you next year, hopefully physically.
Now the session is completed. So now there is, let's say, a virtual coffee break, unfortunately. So next session will start in 15 minutes at 11:45. So hope to see you later in the next session. Bye-bye.
And I think we can start this session for the AI4BPM workshop, which is co-chaired by me and Andrea Marrella, who's also on the screen. We have 3 papers today, mainly on business process prediction and improvement. The first 2 on prediction, the third one on improvement. Before we start, a bit of housekeeping. So I remind the presenters that they have 20 minutes in total, 15 for the presentation plus 5 for questions. Since we can't do the usual way with the paper, adverts and things, and you will be focused on your presentation, well, basically we'll wait until the 15 minutes. And if you go beyond that, I will kindly intervene, reminding you to, let's say, move to the conclusions so that we have time for questions. Then for the audience, the modality for asking questions is the usual in Zoom, so you can either raise your hands or type your question in the chat. Actually, I think that also, let's say, booking a question without specifying in the chat, just entering the "I have a question" message can be very effective because we can keep also the order for that. So you are all invited, if you have questions and you want to ask it directly, to simply add in the chat that you want to intervene. So I think we can move to the first speaker, who's Sven Weinzierl, and the title of the presentation is XNAP, making LSTM-based next activity prediction explainable by using LRP. So,
hello, thank you for a nice introduction. Yeah, my name is Sven Weinzierl. I'm PhD student at the Friedrich-Alexander University at Langen-Nürnberg. Today I present the paper XNAP, making LSTM-based next activity predictions explainable by LRP. The paper was co-authored by Sandra Zilker and Martin Matzner, also from the Friedrich-Alexander University, Jens Prunk and Jörg Becker from the University of Bamberg, and Kat Revoredo from the Vienna University of Economics and Business. Concerning the agenda, first of all, I give you a motivation, followed by a contribution, or our contribution, related work, artifact results, and finally the conclusion and future work. Next activity predictions. Yeah, predictive business process monitoring techniques aim to improve the business performance by providing predictions to process analysts with the hope to supporting them in decision making. For that, deep neural networks showed promising improvements in predictive quality. But predictive quality is not the only thing that plays an important role. Also, explainability to understand what happens is important for adopting a predictive business process monitoring technique in practice. However, the deep neural networks have one problem. They are black box models that is due to their multiple hierarchical learning approach. That means we have nested functions, and because of that, it is hard to understand the way from the data to the prediction. Therefore, we have a problem. The process analyst cannot identify possible intervention mechanisms that might affect the decision making with the goal to secure the process performance. Against this background, we present XNAP. XNAP is an explainable deep learning based business process monitoring technique, especially for the next activity prediction. The main idea of XNAP is an integration of layer-wise relevance propagation. It is a method from the explainable AI domain to make the next activity predictions explainable. For example, if you have a loan application scenario consisting of 4 different activities, as you can see here, A, B, C, D. On the left side, you have a prediction, you have A, B, C, and we predict D. D means decline application. Yeah, the model predicts D, but we don't know anything about which activity contributes to a certain extent to the prediction. On the right side, we have the prediction with an explanation. As you can see here, we have B, the activity B. It is red marked. Red marked means an high relevance, blue low relevance. So we can see here that, or maybe B at details lead to has a high relevance on the decline application activity. So someone can say maybe some details are missing, and that is the reason for, or could be a reason for the decline of the application. Regarding related work of XAI in predictive business process monitoring, we differ between two different types, ante hoc and post hoc. anti-hoc explainability leverages explanation through transparency on different level of a model itself. That means it comes from a model itself. We have to keep in mind previous approaches in predictive business process monitoring, like finite automata or decision trees, are such approaches, anti-hoc approaches. On the other side, we have post-hoc approaches. They try to create explanation in form of visualizations after the model is trained. That is very important here. In this paper, we present a post-hoc approach. If you look at the other figure, you can see that a post-hoc explainability can be differed into model agnostic and model specific. Model agnostic means consider the model as a black hole, permutate the input and look and observe the output. And as you can see here, some approaches have been proposed by researchers in the last years. For example, decomposition, Lime, positional dependence, and connection right. With our in our paper, we propose LRP. LRP can be seen as a model-specific approach because it tries to explain the prediction through a relevant or back propagating through the model, and tries to derive an importance of the input attributes by the learned bytes. But more details are following. In the next step, I want to present the overall picture of the artifact, the technique. The technique consists of two components: the offline component and the online component. The offline component starts with a pre-processing of an event log, metrics transformation of the event log, one-hot encoding of the activity attribute, then prefixes are created, also called as blow-up, and the next activity labels, and finally we construct a structure, data structure, that a recurrent neural network needs, like an LSTM and third-order tensor, and a label matrix Y. Label matrix because Y is one-hot encoded. Model learning, for that we use an BLSTM. BLSTM is an extension of an vanilla LSTM cell, as you can see here from Hobreiter and Schmidhuber, and it maps prefixes. We decided to use a BLSTM, a forward and backward LSTMs. It consists of two parts, two LSTMs, to exploit the control flow information from both directions, from left and to right. And XNAP predicts the next most likely activities. Regarding the online component, similar to the offline component, we transform the running trace into a data tensor and a label matrix. After that, the prediction is created, and the model M returns probability values of all activities and retrieve the concrete prediction P, scalar P, from a vector P through the maximum and with H greater than and less than H. H is here the number of different activity values. Relevance creation is, we determine the relevance values by using LRP. For that, we apply the approach of Aras et al. Or transferred it to the BPI community. This approach was especially designed for LSTMs in context of, or in the sentiment analysis. The output is a relevance value for each one-hot encoded input activity of a data tensor X. So that was the artifact. To better understand what LRP means, the first question is, what is it? It is a method to explain the trained deep neural networks models predictions through something like a reverse propagation. Keep in mind, if you train a neural network, you have a forward path and the backward path, and the backward path you do some back propagation, then the model is trained, all weights are adjusted. After that, we reverse propagate once more to understand or to to determine the relevance values for the input variables regarding the prediction. What is the relevance value? Yeah, it indicates to which extent an input variable contributes to a prediction. If you look at the figure below, you can see RK. RK is something like the relevance values of the upper level neurons, and these upper level neurons or relevance values to these neurons are decomposed to the lower level neurons. That is the basic idea behind this approach. How can we calculate such relevance values? There are a lot of different, the idea is to use propagation rules. There are a lot of different propagation rules, but first of all, we can say LRP calculates these relevance values in 2 steps. First of all, the relevance value of the output layer neuron corresponding to the target class C. That means the outcome of the model is set, and all other the relevance of other neurons is set to 0 because we are only interested in that. And depending on the type of neural connection, LRP defines some heuristic propagation rules. Keep in mind, if you speak about an LSTM, it is not an LSTM at all. It is, we can say, we have an input layer, we have an LSTM layer. This LSTM layer has an LSTM cell, a physical cell that is upfolded over time. And then we have, an output layer. But a layer can be decomposed in neural connections. And if you with respect to the LSTM layer, there are different techniques to decompose it. And if you decompose the layer, there are 2 different connection types: the many-to-one weighted linear connections and the 2-to-1 multiplicative interactions. The first of all, is we compute the relevance messages K to R, the backward, via propagation rule. The propagation rule is here not presented. If you're interested in that, look at the paper, please. Then is followed by summing up a summation term to get the messages for each lower level neuron set J. Then the other interaction type is happens if we have something like gates. In the forward pass, we have something like a multiplication set J equal CG multiplied by set S, and we have a source and a gate, and we can retrieve it if you set R G to 0 and R J is equal RS. So regarding the evaluation, we use 2 different event logs. Regarding the predictive quality, we performed some shuffling randomly. We randomly shuffled the traces to ensure some model generalization. After that, we performed a tenfold cross-validation and measured the predictive quality by the accuracy error and the average weighted F1 score. Regarding the explainability, we demonstrate the explainability of LRP by selected traces for the model with the highest accuracy. That comes on the next slide. And the robustness, we investigated different sizes of traces. As you can see here, for the head-based log, we selected model 9 because it has the highest F1 score and accuracy, and the same for BPI 2019. Here we used the model 10, and I told a lot about I provided a lot of details, but now we come to the results of the explainability. And on the left side, you have a short prefix. On the right side, you have a large prefix with a size 8. As you can see here, the activity C has a high relevance on E. E is the end, so we can say the resolved ticket has a high relevance on predicting the next activity E in traces A and B. So the trace will end since the ticket was resolved. For the other log, if we look at the prefix size 4, the activity C has a high relevance on predicting the next activity clear invoice. So someone can state that the invoice can be cleared in the next step because the invoice received was recorded. Finally, we come to conclusion on future work. The quality of relevance scores depends strongly on the model's predictive quality. That is a hard assumption of model-specific approaches. XNAP performs better for traces with a smaller size and a higher number of different activities. That was the observation that we made during the experiments. Finally, future work. We plan to conduct an empirical study to evaluate the usefulness of XNAP, but also an adoption of the propagation rules of XNAP's LRP to retrieve also the values of context attributes. The idea behind that is we believe that context has a different influence over time. So with the relevance scores, we are able to better understand the context evolution over time. Finally, the comparison of explainability capability of model-specific method like LRP to a model agnostic method. As I presented, most of the approaches refer to post-hoc to model agnostic post-hoc explainability, and it would be very interesting to compare the different types of methods regarding their quality of the explainability. Thank you. That was the presentation.
Thank you, Sven, for your presentation. So let's see if we have questions for you. So for the audience, you can, if you have a question, you can also write on the chat. So we can, that way we unmute you.
I have one if you want, Andrea.
Yeah, there is Andreas Metzger that has a question. So Andreas, you can unmute you and ask the question if you like.
Very good. Hi. Good morning, everybody. Thank you, Sven, for the very interesting work you did. And I think you touched on my question a little bit at the very end already. So I understand that you more or less compute the relevance of the activities or events for the prediction. And then, of course, this ties to the prediction accuracy in how far really this helps you to understand what the model is doing. I have the feeling that it's not only in your work, but maybe in the other works, we miss the point that we're not really sure whether what the model has learned is really an accurate representation of reality, right? I mean, even though this one attribute may have led to the prediction, it doesn't mean that the model really has learned the right, I would say, causal dependencies and not some correlations, right? You have any thoughts on that?
Yeah, thank you for this very interesting question. I totally agree with you. Let me start a bit early or from another perspective. For me, it's very hard to understand why someone tries to learn from a complete event log, because an event log at all has behavior, or maybe some bots or human behavior. And we try with predictive business process monitoring to create predictions. But from my perspective, it seems sometimes a bit hard to fit in a complete event log and to make predictions, but we only interested in some specific, let me say, decision points in the event log. So we can reduce the complexity or the decision space, and through that we would be able to further increase the predictive quality of such models. I think that is one, and yeah, of course, this technique that we presented here, it relies on the predictive quality of an predictive model, and so it depends on it. And if we are able to produce very accurate predictions, the explanations would be better.
But of course, you could also turn it around, right? I mean, it seems your approach is more for the process manager to really understand whether he should intervene or not.
Yeah.
In a similar way, you may also use it for the developer of the predictive monitoring system to see whether actually what the system may predict complies with what you as maybe process expert would also have in your mind, right? And
Yeah.
then maybe detect some attributes which are used which wouldn't make sense, or some wrong kind of prediction based on wrong sequences or attributes, activities, right?
Yeah.
So we always have the kind of end user and developer of these systems, which we could also address.
Yeah, sure. But we also have to think about the form of how we present the explanation to the user. I think that is also a very, very interesting question, and not much research in terms of that. And I think that is also a very interesting direction for future research.
Fully agree. Yeah. Thank you very much. Very good.
No, not at all. Thanks.
Okay, other questions? Because otherwise, Chiara, I think to keep the time.
Dirk had a follow-up question, because mine was very
question.
similar to the previous one, so I'll leave room for Dirk.
Okay. So Dirk, you can talk now if you like. Dirk, can you hear us? Because you are unmuted. Okay, technical. So if you, okay, maybe you have some problem to the mic. I don't know if you want to write the questions if it is not too long. Okay, try again later. Okay, good, nice. Okay, Chiara, I think we can at this point pass to the next.
Yeah, we can move to the next
presentation.
And I think the presenter is Prerna Agarwal, so I invite her to share the screen.
Thank you.
That, great. So can you share the slides?
Yeah, sure. Can you see my slides?
Yeah, we can. So I'm happy to introduce you, and you'll also address the topic of prediction, but in particular how to add, let's say, the contextual factor to prediction with your paper, which is unsupervised contextual state representation for improved business process models. Go on.
Hello, everyone. I myself, Prerna Agarwal from IBM Research India, and today I'll be talking about the work that we have done towards creating unsupervised contextual state representation for improved business process models. So this work is done with my co-authors, Devik, Sushruth, Sampad, and Monica from IBM Research. So I think the previous presentation has already set up the motivation of the kind of problems that we are trying to solve in business processes. So I'll quickly describe the motivation of the work that we are trying to do here. So since we all know that business processes contains finite set of resources, and the presence of other cases in execution can influence the outcome or the next activity or even the time that a case is going to take. So mostly if you look at the prior arts, they mostly encode the intra-case information. So the intra-case information mostly includes just the activity sequence and the information of that particular case in isolation, but they fail to handle the inter-case execution. So the other cases which are running in the system at that time, and also there could be some concurrent activities that may be executing. So we call them as intercase information, and also the features, the data attributes that are present in the event logs. So they are pretty specific to the domain of which the event log is, which is very important to capture their influence on the business process state, because there could be some attributes which may be influencing the next activity you may be landing up, or if you are taking a lot more time in the same activity or a task. So we all know that the LSTMs have been popularly used in the recent work to handle the next activity and next timestamp prediction tasks, because they perform good as compared to other statistical models, but they suffer from long sequence dependency problems. So for the traces, if they have long sequences or long length traces, they are going to suffer from model deterioration at certain point. So for that, we have seen that there exists other deep learning models such as transformers, which are not yet explored for business processes. So what is the motivation of using transformers is, first, it helps us in overcoming the long sequence dependency problem of LSTMs. The other one, it enables us to interpret what the model has learned using self-attention. So the problem here that we are trying to solve is that we need to predict the next activity and the next timestamp prediction, but using the contextual state representation that we propose, encoding not just the intra-case information, but with intercase information and domain-specific attributes. So for this, we consider the event log with a set of traces, and each trace will have an ordered set of events and their timestamps, along with the set of attributes, the data attributes of that particular business process. So given this input, we are trying to predict the next activity and its corresponding timestamp for a partially executed trace in that business process. So just to quickly give an overview of what is captured in the prior art and what is not. So these are the popular methods which uses deep learning models, RNNs, and LSTMs to model the next activity and next timestamp prediction problem. So AVMN tries to embed the sequence information with additional attribute like who are the resources, but they cannot handle numeric attributes or timestamps at all. And they do not consider the intercase features. So intercase features are not seen to be handled by any of the prior art, but except one that is at the end, which also considers some of the handcrafted features which may not be scalable for other domains. So Lin and manual, right? They have similar limitations in the sense that they also do not handle intercase features, as well as they Lin do not consider numerical attributes, whereas manual do handle numeric attributes, but it is specific to the triplets like role, type of the event, and timestamp. And they build specialized and shared architectures, whereas tax gives us an excuse me, sorry. Whereas tax gives us both shared and specialized layer of LSTM predictions, but tax does not handle any of the attributes at all. They just use the activity sequence and the timestamps. So building upon this prior art, what we try to contribute here is an unsupervised contextual business process state representation, which encodes intercase interactions and domain-specific attributes along with intracase attributes in domain agnostic manner, so that this kind of representation can be used, or I'm so sorry. Yeah, so this kind of representation can be scaled for any business process. So for this one, we experiment our representation with LSTMs and transformers for next activity and next timestamp prediction. And we show and demonstrate how do we do model interpretation and explainability using self-attention. So an overview of how the system looks like is that we take an event log which gets passed into a case type labeler. So why do we require case type labeler is something I'll be explaining in the further slides with each module in detail. So case type labeler basically handles different types of business domain attributes. And then we have state aggregator generator, which is going to aggregate all the states of the running cases in the business process to give us the intercase representation. And also we encode intra-case business state representation to be fetched into any of the sequence prediction models. So here we experiment just with LSTMs and transformers, but it can be plugged in with any sequence prediction model for any prediction task. So let's go into the details of each module. So case type labeler is going to accept only the required type of attributes which we may want to parse. So for example, we may have event level attributes which will change within a case as well. And also we may have case level attributes which are common across a case. And we also have concurrent activities in a business process. So case type labeler is going to specify if we want to handle only the categorical type of features, or do we want to handle both categorical numeric types of features, or what type of features do we really want to handle? So here we majorly handle 3 types of features: categorical, numerical, and time-based attributes. So categorical attributes are represented as simply one-hot vectors, but if we have concurrent activities, then the value at which a concurrent activity is getting executed will be set to 1, like more than one value will be set to 1, depending upon what is the value of the categorical attribute of each concurrent activity. Similarly, for numerical attributes, we normalize them between 0 to 1, but if we have concurrent executions, then we have to bucket the numeric values into a set of buckets, and then we assign the value of each running case or each concurrent cases to 1 in that bucket. And then we use the timestamp value to create this time attribute vector, which is consisted of the time elapsed since midnight and what was the weekday when the case was getting executed, the time elapsed since the last activity or last event, and what is the time elapsed since the case has been started. So all these times are taken in seconds to form this time vector. So this is just to model the domain specific attributes that we have. And then how do we get the intra-case representation for an activity is the unification of all the attributes that are present, be it numerical, categorical, or time, and concatenate their feature vector representation for any prefix P, consisting of n partially executed activities. So this is how we obtain the intra-case representation. And moving on to how do we get the inter-case representation is something we first of all define the duration of a case trace. So if we have a trace Ti getting executed, its duration interval will be defined as the start time and the end time, which is going to define the minimum and maximum time of the duration. And the set of ongoing cases will be the set of all the cases which are falling in this particular duration time period. So once we have these ongoing cases, so what important of these ongoing cases will be the last activity at which the ongoing cases are there and which are in execution. So we take the vector of the last activity and encode it just like we encode the intra-case representation of an activity to get the set of all the context vectors that we have, and that forms the ongoing cases, which we define as the context of a business process state. So once we have the set of running cases, then how do we aggregate them to form a single context vector is we employ 2 methods. One is by pooling, the second one is using attention. So in pooling, we first of all embed the vectors using a feed-forward network to have a single dimensionality of all the vectors. And then for an activity, we basically aggregate all these running cases, which you see here, either by max pooling, sum pooling, or min pooling to generate the intercase context vector, which can be then concatenated with the final vector for any prediction task. And with attention, we use Bernardo attention because it considers all t-1 states at any time t, which they have seen to create the context vectors and to learn the attention distribution, that is the weights of the importance of each activity or each feature that is getting executed. And then once we determine this weights or the softmax, we multiply them, or we take the weighted average with the vector that we have to get the weighted sum, and that forms the intercase context vector. So this is how we get the intercase state representation. And then how do we use it with LSTM or transformer or with any prediction or any prediction model is that we have shared layers and some of the specialized layer. We use a combination of both of them. The first few layers, like the n layers, which will be shared, will have the intracase representation because it is going to encode what is being executed at each activity. And then for the specialized layer for activity and timestamp, we are going to feed in the intercase state representation either as an attention or as the pooling vector that we obtained from the previously explained methods. So then we get the activity prediction from the specialized layer and the time prediction from this specialized layer. So the datasets that we have used for the experiments are the popularly PPR challenge datasets and help test dataset. So we have used PPR challenge 2019 dataset because it hasn't been used so far by any of the work done, and it would be good to evaluate our approach on these because it contains a lot of business attributes. We also create a synthetic dataset from a simple PPM, and you can see here, like we have three tasks, task 1, task 2, and task 3. So for first case, we assume that task 3 is independent of the execution of task 1 or task 2. And in the second variant, we assume that the task 3 is dependent upon either task 1 or task 2 or a combination of both of them. So we use only the prefixes of length 2 and above, and we divide the dataset into train, validation, and test splits in the ratio of 70%, 10%, and 20%. And the loss function that we are using here to train the LSTM and transformer model is the sum of negative log likelihood for the next activity and mean average error for the next timestamp. And we use grid search over the hyperparameters to obtain the best model out of it. So the number of shared layers that we want to use here, the number of layers that we want to use for prediction, and the number of heads. So for transformer, we use multi-head attention. So how many number of heads are we going to use is something which is also determined by grid search and the dimension of the vectors that we want to experiment with. So the optimal hyperparameters are used as a set of one shared layer, one layer for prediction, 4 heads in attention, and 128 dimensions for transformer. And for LSTM, it would be, so the number of heads won't be one of the hyperparameters, it would be just the shared layers of prediction and dimensions. So it forms 1, 1, and 128 for LSTM. So with this, if you can see in the table, we have experimented with a lot of variants of our own model itself. Like we experiment with LSTM along with mean pooling of intercase vector, LSTM with some pooling, max pooling, and then if we employ attention over LSTM, what would be the performance of the next activity prediction accuracy and the timestamps in MAE for all the 4 data sets. So we see that attention outperforms the other pooling mechanisms and the baselines. So baselines are the popular ones, FMN, TAX, and manual. And if we see that, we compare it with the kind of accuracies we are obtaining for transformer models. So we see a similar performance of LSTM in transformers because of the not very large lengths of the traces that we have. So if we have larger trace lengths, the transformer is going to start performing better than LSTMs. And for BPI 12 and 2019, we have larger trace lengths. So therefore, if you see, the performance of LSTM starts decreasing and the performance of transformer model starts to increase. And for other data sets, they are similar because of shorter trace lengths. And a higher improvement on help desk and BPI 13 datasets is observed as compared to other baselines because of presence of a lot of domain specific attributes. And we see overall a significant improvement with respect to the other models that are there, which doesn't employ domain specific attributes and attention to model the intercase executions. So in order to understand,
your time is almost, is up. So I think you should, quickly move to the conclusions to leave time for questions.
Sure. So I'll just take a minute to explain the interpretability. So if you see, if in the chart, if you have the numbers concentrated on the diagonal, that means the attention is only on the same activity. Otherwise, if you see the distributed ones, it's more dependent upon other activities as well. So that is how we interpret these graphs, and more details you can look in the paper. So just to conclude, we propose an unsupervised technique to obtain the contextual state representation, which beats the state-of-the-art models and which also helps us analyzing the impact of other ongoing cases and domain-specific attributes. And this work can also be further extended to incorporate features from unstructured comment information that we have in event logs. And also it can be used for other tasks like outcome prediction, trace clustering, and so on. Yeah, so I'm open for questions.
Thank you for your presentation. So it's time for question now. Is there some question from the audience? Chiara, do you have some question?
Well, yes, but the other Chiara is one, I think. I see in the chat.
Yeah.
Okay.
Yeah. I have one. Thank you for the presentation. I would like to ask you whether you have seen this other way of, I mean, there is a follow-up of the work by Senderovich et al. And I would like to ask you if you have seen this work. I don't know if you have done it, but what I would like to ask you is, I mean, I think it would be interesting, more than a question is a suggestion, to use that unsupervised way of retrieving, I mean, not domain context way of retrieving interface feature there, and try to apply it to LSTM for the prediction of the next activity and for the prediction of the remaining time. So I want to ask you if you have seen that work, and if you don't have it, I mean, it's just a suggestion, and if you think that it could be also applied other type of interface features with another mechanism to the LSTM that you propose.
Yeah, so I found it, I saw that work, but I found it to be another limited to certain type of business processes. So here we wanted to, you know, have a generic kind of representation which can scale for any business process with any set of domains by providing flexibility to have an automated way rather than handcrafting the subset of features, right? So maybe, yeah, I can again go through and see if we can scale it with respect to the kind of representation we are trying to achieve here.
Okay, thank you.
Thank you. Thank you for the suggestion.
Thanks, Chiara. Now, the other Chiara, if you have a question, I think you can ask.
Well, it's more a curiosity rather than a question, because I mean, you basically what you do, you incorporate the context, let's say, in terms of information you already have in the trace in your event log, right? But another way of looking at context could be also to inject external information, so information that is not in the log, but information that suddenly you somehow have. So do you see also a way of expanding your work in this direction?
Yeah, I think what we want to see more is towards goal-driven predictions as well, which considers the external factors which may change. But I think with that, the major problem is with like how to define those external factors and, you know, how to incorporate them is a secondary thing, but how to really identify the right external factors. And again, that would be more like a domain dependent thing. So yeah, we have some thoughts there, but we haven't reached to much, you know, progress there.
Thank you. So I believe we can move to the final speaker, to the third speaker of this session, and move also to root cause analysis. So Manat Sadat Wafari, if you are there, you can, yeah, you're there, great. You can share your screen.
Yeah.
Presentation. Okay. Excellent. So basically the floor is yours and you will present us your work on root cause analysis in process mining using structural equation models. Please.
Thank you very much. Thank you very much. I'm Mahnaz Sadat Kafari, a PhD student in RWTH Aachen, and this is a joint work that I'm going to present with Professor Will van der Ost. I'm going to start with the motivation that why we need to do root cause analysis using structural equation models. What structural equation model is going to add for us? I start with the three simple facts. First of all, we can see a lot of correlation, very nice, strong correlation between features in the data when these correlations are not causal. Here you can see three examples, and I myself like the middle one, the one that you can see a very high and strong correlation between the age of Miss America and the number of murders by steam, hot vapors, and hot objects. The other fact is that the basic of almost all of the machine learning techniques are correlation, not causation. Doesn't matter how complicated is the technique, we always look at the correlation, not always, but almost always. And the third fact is that the process mining is not different. Even in processes, we can find a lot of features that they are highly correlated, but not causally related to each other. This fact come to a picture when we look at some tasks that need root cause analysis and some tasks that we need to do, and we need to perform some change in our processes to make some difference in the outcome of our processes. For example, we have a problem in our process and we're going to solve it. Then definitely correlation is not enough. First of all, we need to see how different features in our process have causally are causally related to each other, and definitely we prefer to have it in such a way that is graphically and nicely and human friendly visible. And secondly, we want to know how strong is each of those causal relationships. And the third, we want to see the effect of any intervention in our system. Definitely, we can do that with randomized experiment, but as we know, it's not possible. If not definitely possible, but quite expensive in the domain of processes. We cannot change whatever we want in our processes. We may solve very, very strong negative effects in other areas of our process. Then we need to see the effect of intervention. All these three things can be done with the use of structural equation models. Let's start with another example. We have a process that implements some software for its customers, and they are not happy with the implementation duration. By implementation duration, we mean the duration of two activities, development and test. And they think that these three attributes, priority, the duration of product backlog, and the number of people working on that project has a causal effect on the implementation duration. Definitely, if they're gonna take some action to make the implementation duration shorter or longer or whatever changes, they need to the action that they are going to take is highly influenced by the causal relationship that exists among these features. There you can see three different causal structures. The first one, if they're going to act according to the first one, they will change the number of people working on that project or the priority, but they know that changing the duration of the product backlog doesn't change the implementation duration. In the second one, they may decide to change any of these features because the three of them has a causal effect on the implementation duration. And in the third one, there is even another feature called the hardness of the case that may have a causal effect on the implementation duration, and they can influence on the implementation duration by intervening on the hardness of the cases, priority, and the number of people working on that case, but not the duration of product backlog. Let's imagine that the third one is the right one. In fact, this graph that you already see here is a causal structure graph. The causal structure graph is a graph that each node of it is correspond to a feature, and there is an edge between A and B if A is a direct cause of B, and also this graph needs to be a tag. Some more thing about this graph is that the nodes that are direct causes of a node are called its parents. For example, the parents of implementation duration are hardness and team, and the number of people on a team. And the parents of the number of people in a team is the priority and the hardness. This graph is nice. It shows how each feature influences another feature, but it would be even nicer if we could have said how strong is each causal relation. For that, we can think of sort of modeling each feature by the value of its parent. Something like what you can see on the left side. For example, you can see that the duration of product backlog is 10 times the hardness plus some noise. This function can show that how strong is the causal relationship. This set of equations is called the structural equation model, and it do the three things that we wanted as our goals. First, it shows the parents, those features that has a direct causal effect on every attribute, plus the strength and the effect of an intervention. There's a small technicality that the noises need to be independent of each other, but it's not already important. For finding the causal structure model of some attributes in a process, we go through this process. First, we enrich the event log with adding some attributes to it, and then according to the problem that we're going to change, or the feature that we're going to change, or problem that we're going to solve, we create a data table that we call it situation feature table. Then we use a black box, a magical black box that give us sort of a graph that shows to some extent the causal structure graph in among the features in our data. In fact, this magical box, this causal structure inference algorithm is not perfect, especially it cannot find the directions between different nodes, the direction of the causal relationship. And for that, we need to use domain knowledge. When we find the causal structure of our data, we can model every node by its parents and find the causal, the structural equation model of our data. As you can see, for the enriching the event log, we can use a lot of different attributes. For example, the trace duration, event duration, deviation, and many more. Now I'm going to mention how we're going to create the situation feature table, and for the rest, I'm going to demo the plugin that we have implemented in a Pro. For the, we wanted this work to be as general as possible. So for the problem that we're going to work on and find its root causes, we work on three different sorts of problems. We call them trace situations, event situations, and choice situations. A trace in the domain of process mining, the data is stored in the form of events, and each sequence of events is called a trace. Here, imagine that every colorful box is an event, and this sequence of events is a trace. A trace situation refers to a problem in a trace, for example, a delay or the duration of a trace. Then we map every trace, the information that we extract from every trace, to a row in our table. When we're looking on a problem in events, for example, the duration of activity purple, then we have we are in the event situation domain, and here every prefix of the trace that ends with that purple activity is mapped to a row of the table. And for outcome of a choice list, and every time that that choice happens, we add a row in our table. Okay, now I can go to the demo. For the plugins that we have implemented, the input is the event log, the PetriNet model, plus the replay result, the conformance checking result. And then we can run the plugin, which its name is root cause analysis using causality graph. And here in the top right, you can see you can choose the kind of situation, the kind of problem that we're going to deal with. For example, we're going to work on an event situation. Here we're going to, for example, see what caused the remaining, what has a causal effect on the remaining time of activity T10. Yes, we choose the activity and then the remaining time. For that, I'm going to investigate the effect of duration of this activity. T4 and T6 on activity duration. Okay. The table is created. Now we can do the search. Oh, I made a mistake. Yeah, I should have chosen the data to be continuous, not discrete, but I didn't do that. It's already, I think it takes a long time till it comes up. Takes a little bit of time. Oh no, okay. We need to make it continuous because the data is continuous, and then do the search mean it's okay. Here we need to remove the null values. And then here you can see that it found some causal relationships, this magical box that here for that we use GFCI algorithm, but the direction are not that perfectly correct. For that we need to use domain knowledge, because I know the precedence of the attributes. I can say it's going to be something like this. I'm going to generate the final graph and then do the estimation. When I do the estimation, I can click on every node and I can see an equation, the fourth line, that shows how strong is the effect of these causal relationships. Or if I can do the same with choosing, for example, for a trace situation, I can choose something like deviation in our traces. And then here, instead of, I can look at the influence of choosing the resource, create the table again, okay. Okay, now the data is, as you can see, it's discrete, not continuous. And then I can do the search and see what is the result. Again, this magical GFCI algorithm find the causal sort of class of causal structured graphs that shows the we need to turn it to a DAG. this one. Okay, and now after doing the estimation, that's gonna take a little bit of time. If we click on any node, we can see the effect of intervening on any of these nodes. For example, here I click on this node, and the meaning of the values is that if I force the value of this feature to be resource unified in 1/3 of the cases, we will have no deviation, and in 2/3 of the cases we will have a deviation.
Manas?
Yes.
You also used your 15 minutes, I'm afraid.
Okay,
so
it's done. It's already done. And yeah, that's my presentation. And the goal is to find this causal structure for the data that we're going to have, and we wanted to make it in a general, as most general way as possible. So we're going for these three kind of situation: trace, choice, and event situation. And we use the GFCI algorithm. That is one of the best algorithms for the causal structure inference to do the causal structure inference, and then at the estimation that we can use it to find the sum of our data. Structural equation model. Thank you. Any question?
Thanks for your presentation. So are there questions from the audience? So, okay, there is Marlon that has a question. So Marlon, you can unmute yourself and you can ask the question.
Yeah, thank you. Thank you very much for this presentation. So what I was wondering is to what extent what you are proposing requires some interaction with the analyst or input from the analyst. Like, is this really, do you have to pre-process the log, or do you have to identify situations manually, etc.? So yeah, what does the user needs to do to get this running from a raw event log?
From a raw event log. For the input, as you can see, we use the event log and Petronet plus the conformance checking result. That's one part that user needs to do something. And the other thing is that the user is the one that is responsible for choosing the set of attributes that has a causal effect, or the best set, maybe something bigger. But some superset of the set of attributes that has a causal effect on the attribute that we want to investigate on it. Because
so you need the user to provide you, but in the way you have a hypothesis testing tool. So you have the user has to provide you the hypothesis, and you give a methodology for validating that this hypothesis I have, that there are these causal relations actually exist, and to quantify the effects.
Yes, and how strong is, yeah, that's the part that user has to work on. Yes.
Okay. Other questions?
Well, somehow I have a follow-up question, in the sense that for instance, in the first talk, we have seen that now there are tools that, through the concept of explanation, for instance, find correlations, right? So you could think of these correlations as also an input or a set of candidate things that you could then test whether it's further, let's say, consolidated by your, causality finder, if you want to see that way. Would that be a possible use case for your tool?
For that one, if you're going to say, you can use those attributes that has a correlation with the, for example, here with the deviation or with the problem that we're going to work on, as a set of input attributes. And then you can say if there were a causal relationship between them, yes or no. And there's something else, that there's a possibility of finding some hidden variables that has some roles, and these things you can be notified about them with the type of the age.
So someone else, but perhaps if I may add to the question to Chiara, like an essential step is the selection of the features that you use as input for this model. And what you have implemented basically does everything. It is able to detect correlations and is able to automatically distinguish correlations from causalities. Then comes up with this graph, and the user can edit it based on domain knowledge. So it includes everything, but the step is relatively expensive in terms of computation time. So what you could do is that you could use correlations, which is much cheaper to detect, as a kind of pre-processing step to guide the user in selecting the features. And I think that is how these two things fit together.
Yeah, but the thing is that sometimes you can find a set of attributes that have a causal. The combination of those attributes have a causal relationship. Not every one of them, and in this case, this algorithm can find them.
Thank you. Any other question from the audience? No, I think we can.
Just one simple question. Yes, just about the context of applying this approach. Is it the only context in the feature selection as being mentioned, or even it can be applicable in the process improvement? Or
the application of this work, you mean? Sorry, I didn't. If we're going to think about the application, I think the main application is process improvement.
Yes.
Yes. And what was your question, please? I didn't get that.
Yes, yeah, this is actually was my question. So it is the context of the application is the process improvement.
Yes, exactly, because you can find what attribute has a causal effect on the attribute that we're going to change, and how strong were the effect, and what's gonna be the result of an intervention. You can have all these three things together.
Okay. Thank you.
Welcome.
So yeah, I believe our time is up basically for this session. So Andrea and myself, we thank all the speakers and the audience as well, and well, enjoy your lunch break.
Okay, just to say that the afternoon session will start at 1:45, so in 45 minutes. So see you later, and thanks to all.
And you have to check on another link. Okay, we have a different link for the afternoon session, not this one. Okay, just to clarify.
Thank you.
Thank you.
See you later.